the last part of this seminar series here, I will talk about the Liouville superoperator formalism, and I will limit myself on how does the structure look like and how can I set up the basic equations. So I will not give any example calculation or anything, but I think it's important to understand what is the basic build-up of this formalism and what does it do and how can you work with it. And so let's start with the basic idea. So we will look at the Liouville superoperator formalism. And while in the spin density operator formalism, we have a rho of t, which is the propagator u times rho of 0 times the propagator dagger. When we look at it, then this is actually a square matrix equals a square matrix times a square matrix times a square matrix. And it's very well suited to tackle all the problems that we have when we look at coherence evolution or polarization, how it's converted. But for relaxation properties, it would be much nicer to multiply the spin density operator only with a specific relaxation rate. This way one can give directly some number for relaxation strength and simply apply it. So it would be better for relaxation treatment to have a vector that is simply the square matrix times a vector. And now, how can we do this? And the idea of this Liouville superoperator formalism is very simple. You have your rho, which you can write down as the components rho alpha, rho beta, rho plus, and rho minus. And now you simply say you restructure everything. You say you write it in a vector. You say you have rho alpha, rho beta, rho plus, and rho minus. And that's it. That's all you do. Unfortunately, it has some consequences with the mathematics behind. So we know that rho dot equals minus I, the commutator of H with rho. And that is, as we know, minus I, H times rho minus rho times H. Now to bring everything in a nice equation, like to construct this matrix that connects the two vectors, there we need to think about something, and essentially the solution is we create the so-called Liouville superoperator, and that is defined as H with a double hat equals simply a Hamiltonian in a commutator with an operator that will come instead of the dot. So in this way, we can now write the Liouville von Neumann equation. We can rewrite it as rho dot, and we write this also with a hat to indicate this is the superoperator formalism. And this rho hat is now H double hat times rho hat, which is, of course, forgot the minus I, I'm sorry. So minus I H double hat times rho hat, like this. So now, how can we get the form of this Liouville superoperator? We've seen here this reordering. This is just this rho hat, and now we need to see how do we write this Liouville superoperator. And its components, in essence, is described by the individual expectation values. So if you have a superoperator S and the element Rs, then this can be written as the basis of BR times the superoperator acting on the base operator Bs. And that is simply, as you know, the trace of BR dagger as superoperator Bs. And so when we look at the Hamiltonian superoperator, there the component Rs would be the base operator Br times the Hamiltonian superoperator Bs, and that would be, in this case, the product of Br times H commutator Bs minus Br Bs commutator H. So what does this mean? Let's construct an example. So our Hamiltonian is simply omega I times Iz, or omega 0 I used before, doesn't matter. And now I write any density operator rho just in coefficients of its base operators. So I write rho equals rho alpha times I alpha plus rho beta times I beta plus rho plus times I plus plus rho minus times I minus. And we know this is the typical matrix rho alpha, rho beta, rho plus, and rho minus that are also introduced above. And these I's, they are the base operators, B that we introduced here for the calculation in essence, B, R, and B, S. And now with these coefficients, we kind of do the calculations and they're placeholders, which in the end tell us at which position we have to write what value. So I hope it just becomes clear when we do it. So first we calculate H times rho, and that's simply 1/2 omega I minus omega I 0, 0 times rho alpha, rho beta, rho plus, rho minus. And when we calculate this, then this is omega I times rho alpha, omega I times rho plus, and below we have minus omega I times rho minus and minus omega I times rho beta. We also calculate rho times H, which is same thing, just the other way around, 1/2, and now rho alpha, rho beta, rho plus, rho minus times omega I minus omega I, the two zeros. And what we get here is now, oh, I forgot the 1/2 up here. So here it's 1/2, and then we have omega I rho alpha and minus omega I rho plus. Then we have omega I rho minus and minus omega I rho beta. Now if we calculate H rho minus rho H, then this is simply 0. The first element cancels, the last element cancels, while the other ones add up because they are of opposite sign. And so we have 0, omega I, rho plus, minus omega I, rho minus, and 0. And it's clear in this position, it's omega I, rho plus times I plus and minus omega I, rho minus, I minus. And so what we can tell from this is simply that we have one element, and that is I plus, that is super operator working on I plus, that this value is omega I, because we started with rho plus indicated by the placeholder rho plus, which means we started with I plus spin density operator, and we ended up in I plus. This is the expectation value from I plus to I plus, and for the Hamiltonian here. And this is apparently the prefactor omega I. And the same thing, of course, holds true for rho minus, I minus, where we have minus omega I as the element. So we can also write I minus had I minus must be minus omega I. And this we can now put into the equation. So what we have altogether is our rho dot, which would be rho alpha dot, rho beta dot, rho plus dot, and rho minus dot. That equals the double head Hamiltonian times the head rho, and that is then the matrix. And the matrix has only two elements that are non-zero, and this is omega I and minus omega I. All the others did not give any result in the calculation. And here, of course, we have again the rho alpha, rho beta, rho plus, and rho minus. So knowing everything, we can now write in this way the Liouville superoperator Hamiltonian as this 4x4 matrix for a single spin. So this is the Hamiltonian that we had for the chemical shift evolution. Means this is omega I times I z in superoperator formalism. Very easy to do, but I want you to learn a bit more or to connect it with other things. And so this is one 4-vector, and this 4-vector is the one that's usually used with alpha, beta, plus and minus. However, we have now another set of base operators that fulfills everything. And how about that? Like we have the same H, which is omega I times Iz. And what if you take a base that consists of Ix, Iy, Iz, and a unity matrix? Let's see. We can write our rho to be 1/2, and this is rho z plus rho 1, rho x minus I rho y, rho x plus I rho y, and rho 1 minus rho z, which you can also write, of course, as rho x times Ix plus rho y times Iy plus rho z times Iz plus rho 1 times 1. Now we do the calculation again. There we have altogether then 1/4 omega I minus omega I times the matrix that results in omega I z plus omega I rho 1 omega I rho x minus omega I omega I rho y minus omega I x minus omega I rho y and minus omega I rho 1 plus omega I rho z. Then rho times h understand what I mean with this, and times omega I minus omega I 0, 0. And there we will end up omega I rho z plus omega I rho 1 omega minus omega I rho x plus I omega I rho y, and we have omega I rho x plus omega I rho y, and here we have minus omega I rho 1 plus omega I rho z. So then we have now the difference, it's 1/2, that is 0, 0 minus omega I rho x plus I omega I rho y, and down here we have minus I omega I rho y. So what we see now is that what is originally rho x has now the structure of having a positive component here and a negative component here, which means we can now build this up as IY. So this is now something for the operator IY because of the sign difference. While the other part here is rho y, it starts from y, but it has minus I omega I and minus I omega I, both the same prefactor here, which means it is a prefactor to the basis of Ix. So what we have then is minus I rho y omega I Ix plus I rho x omega I Iy. Ix is 0, 1, 1, 0 times 1/2, and Iy is 1/2 0 minus I. So we have these two operators, and so now when we look at this, we can write the Liouville super operator equations. I start with a 1, then Ix, Iy, Iz, and of course we have the time derivative, and that shall be, can take the minus I out, and so we have 1 Ix, Iy, Iz, and then we have 0, 0, 0, 0, 0, I omega I, 0, 0, 0, and then minus I omega I, 0, 0. So this is our Hamiltonian when you look in this space. And of course the minus I can be taken in. So this is then minus omega I plus omega I times the coding. 1 Ix, y, Iz. So great. We know now how to convert an Hamiltonian into the superoperator formalism in two different bases. Why do I do this? The second base even. Well, I tell you for H equals omega Rf x Ix, the superoperator is going to be 0 minus omega Rf x omega Rf x 0, 0, 0, 0. And H equal omega Rf y, the y component times Iy. There H will be omega y minus omega Rf y 0, 0, 0, 0. So when you combine all of them, total rotation superoperator, you get the operator of the form 0, 0, 0, 0, 0, 0, 0. And then inside we have the diagonal, also zeros. Then we have minus omega I for the offset. We have omega Rf y and minus omega Rf y for the y pulse, and minus omega Rf x and omega Rf x for the x pulse. And whenever you saw fundamental equations in NMR, you have seen a very similar pattern already. Well, now we, in addition to this, we also would like to install relaxation. We can do it the very same way. We take this equation, so we have this rho 1, rho x, rho y, rho z. Take the dot over everything, and that will be now a matrix with relaxation coefficients times here 1. So we can define now relaxation coefficients for every of the 16 fields. We can define the relaxation rate, how it relaxes. But this is a closed system. It contains all spins that we have. So we do not remove any spins. Even with relaxation, we do not kill any spins. We do not lose any spins. There must be somewhere. So, you know, T1 and T2 relaxation. So T1 relaxation builds out of nothing, slowly Z magnetization. On the other hand, T2 relaxation, you have magnetization that precesses and then it slowly dephases and ends up in nothing. It should be clear to everyone that these are two independent processes. The magnetization vector, it's dephasing, and then there is nothing, and then slowly something is growing up. And where is it coming from? It's clear. It's the huge spin reservoir that we have of these isotopically distributed spins. Where are they here in this equation? Does anyone know? Where's the spin reservoir? In the 1, exactly. It's the 1. So when we look at the populations here, the real populations at a 1 gigahertz spectrometer solution state NMR without hyperpolarization, thermal equilibrium, then this rho 1 would be 99.99% of all spins. And this rho x, rho y, rho z would be just the very little bit that we detect. We have now the big reservoir of spins. And now it's like in kinetics. We lose something. We have some magnetization that we lose with a relaxation rate minus Rz, let's say, and it must go somewhere. Where does it go to? Maybe I should have started with rho x, then it would be clearer. You can also here minus Rx. Where is it going to? To the 1, of course. It's dephasing. That means it's getting part of this big reservoir. So if you do minus Rx, if we lose Rx, then this must end up in 1. So what we have to do is we have to do a plus, which means plus Rx somehow. And of course, we lose R1 and we will put it to Rz. So we have here plus R1z and here minus R1z. But then we have minus Ry plus Ry minus Rz, also plus Rz. And then there is also something that is known in literature, which is near field induction. There's actually a theory about it that our spins, they live very long when they precess. And that is not just the spins that are initially excited, but spins that actually take with them close by spins. So near field induction to other spins surrounding, and that enhances the length of our FID. Because this also happens, so out of the reservoir, we also have, well, I write it here, also minus R1x and minus R1y, which will end up plus R1x and plus R1x. So magnetization out of nothing comes to our spins near field induction. Very nice effect. And then there may be even more relaxation components that you relax from y to x and from y to z, etc. These are the other 3 components that are missing here on both sides of the diagonal. I leave it like that for the moment. Just want to tell you there are relaxation rates towards the unity, towards the spin reservoir, and from the reservoir to the rest. Everything can relax into everything. And the dominant values, of course, are this Rx, Ry, Rz, and the others that I was mentioning, especially this R1z is, of course, the driving force to restore our equilibrium magnetization. So this is all combined here, all relaxation processes. And because this R1z is slightly more efficient than the Rz relaxation, that's the reason why we build up equilibrium magnetization. And so with this, we can directly involve everything that we do. We have this now, but these 2 equations can be combined. And we can also say that minus Rx equals minus Ry, and that is usually written as minus 1 over T2, and minus Rz is written minus 1 over T1. And as NMR spectroscopists sometimes are a bit ignorant, they of course will simply not show this unity operator. Well, then you have the difficulty that this is not a closed system. You need to reintroduce something. And what people do, they rewrite this relaxation operator thing, they rewrite to rho x, rho y, rho z, dot, 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 equals now only a 3 by 3 matrix. times rho x, rho y, rho z. Then we have minus 1 over T2, minus 1 over T2, minus 1 over T1. And to correct this missing relaxation rate from the reservoir to the actual spins, you need to introduce a correction, and that is the equilibrium magnetization, which is considered to be the Z magnetization, which is here minus rho 0. But maybe you now understand where all this comes from. These relaxation rates are nothing but exchange rates in kinetics. It's the same thing. You cannot remove anything. You always have to have as much plus as minus in this relaxation or exchange matrix. And because we leave out the big spin reservoir, only because of that, we have here relaxation rates that are only minus, that are only dragging things away without building up anything. And this is reintroduced artificially by this rho 0. Yeah, so we have this, and now we should, of course, include also the rotation into the matrix. And we can do that easily by simply copying. So that's minus omega I, omega RF y, minus omega RF y, omega I, minus omega RF y, and omega RF x. So this was an x, sorry. And now some of you at least should recognize this equation, what we have written here. If you say now magnetization would be mx, my, mz, and that corresponds to rho x, rho y, rho z. When we say gamma times b is just gamma bx, gamma by, gamma bz, and that is omega I, omega RF x, omega RF y, omega I. And if we say R equals 1 over T2, 1 over T2, 1 over T1, and M0 equals 0, 0, M0, so the vector equals 0, 0, rho 0. If we take this, then we can write the upper equation as d of the dt m equals gamma m cross b minus r times m minus m0. And that equation is the shorthand notice of the famous Bloch equation. So essentially meaning that for a single spin, this Liouville superoperator formalism is essentially identical or pretty much equivalent to the Bloch equations for a single spin. And I told you now what are the sequence behind this equation, why you need to have this equilibrium magnetization. For example, it's because we neglect a lot of these relaxation rates that are present. Now, from this is for a single spin. The Bloch equation is limited to spins without coupling. But with the Liouville superoperator formalism, we can now look at arbitrary spin systems. The spin density operator is included. It's just rearranged. So in the end, it's a kind of a spin density operator formalism, just in a different form. So for higher spin systems, it's common to sort populations and coherences, as you will see. And I will give you just an example how the basic equation looks in general, which form it is. And I will not go into detail how the corresponding Hamiltonians, etc., look like, just that you understand how everything is built up. What does the formalism look like? So we have an equation, and that of course means we have d over dt. Then we have a large vector, and then this ends up in a matrix that is even larger, times again a vector. And now we want to fill the vector elements. And let's start. So I go back now to the alpha, beta, plus, minus base operator system. And so the first one in a two-spin system would be I1 alpha, I2 alpha. Then, of course, I1 alpha, I2 beta, I1 beta, I2 alpha, and then I1 beta, I2 beta. These are the populations. I don't want to write everything, so I will continue now just writing alpha, beta, plus, minus, if I may. So next we have plus, minus, and minus, plus. Then we have alpha plus, alpha minus, beta plus, beta minus, plus alpha minus alpha plus beta minus beta. And then we have plus plus and minus minus. And I'm sure you understand the colors that I used here. In lilac, we have populations. In red, we have zero quantum. In blue, we have single quantum. And in green, we have double quantum coherences. So that's the sorting that you have. And of course, we have everything the same on the other side. So because I have the pen ready, I will do it the other way around. So like this. And now what we get is the so-called red field kite, as we see in a moment, because when you do nothing, relaxation as well as development of magnetization, you usually keep your quantum number, which means populations can be interconverted into each other. Single quantum can be interconverted into each other. Zero quantum and double quantum, they all can essentially only be interconverted into each other. And we have these diagonal elements and this kite for the populations. Then we have two elements here. Then we have 3, 4, 5, 6, 7, 8, and harmonic height here. For the single quantum, then we have 2 more for the double quantum. And this looks almost like a kite when And that's why this is called the Redfield kite. It comes from the Redfield theory. So this is the structure of the Hamiltonian and the relaxation operator in particular. Of course, the kite is left when we apply pulses. When we apply pulses, we can change single quantum into zero or double quantum. But just from the natural Hamiltonians, from the so-called drift or evolution Hamiltonians, you cannot change between the different parts of the kite. And so if we have this ordering that is usually used, then we can write down maybe the general equation, and that is rho dot of t equals minus I Hamiltonian double hat times rho hat of t minus gamma superoperator of rho of t minus rho 0. And that pretty much resembles the Bloch equation. Also here, you indeed take the equilibrium magnetization as rho 0. You neglect the 1 usually, the reservoir. And this relaxation matrix gamma, just to mention that, gamma. This you get out of Redfield theory, out of the interactions that you have. You can show that for relaxation to take place, you always have pairwise interactions. That means you end up with a double commutator and higher order terms, which involve a 4 times commutator, etc. But these you usually neglect. So the common relaxation theory predicts that we have this 1/2 times sum of q and q prime, sum over p and p prime, j, q, q prime, omega p, q prime, times a, p, q prime, commutator, a, p, commutator, rho. Nice formula. Well, if you want to know what's behind it, then I just recommend you the lecture given by Art Palmer. He really digs into what these coefficients are. Just to give you some hints, q and q prime are indices over all interactions and individual irreducible tensor components, also referred to as the tensor alphabet, for example, and it's spherical harmonic functions in the end. Then you have p and p prime. These are indices for eigenvalues of the irreducible tensor components of the interactions. Then you have J of omega, that's the spectral density function, which is Fourier transform of the correlation function describing rotational diffusion. Rotational diffusion, I hope that's clear what I mean with this. Molecules that have Brownian motion So they do zigzag movements, but not only, they also rotate. And this rotation is a statistical process. It's a statistical diffusion process, and it's called rotational diffusion. You describe statistical properties with a correlation function typically, and when you take the correlation function and take the Fourier transform, then you get this spectral density function. And last but not least, the A's. These are the operators of the individual interactions represented in, surprise, irreducible tensors. So just to give you an insight, there are many, many components that you have to put together, and then in the end, you get this relaxation matrix, and this relaxation matrix is then put into the Liouville superoperator equivalent to the Schrödinger equation in the end. And with this, you can calculate everything, including relaxation, where the relaxation part is a classical approximation, where the rotations that we see are just treated classically. But so far, we could always explain everything with this type of equation. There was nothing that I'm aware of that could not be explained with this equation. And with this now, you have the tools. And be aware, spinach, for example, only uses this type of formalism. Yeah, it takes the spin densities and directly puts them into just columns, not matrices, and calculates with this. That's also why the operators there are L, typically for the Liouville operators, not I, but I usually use for the normal spin density matrices. And yeah, I mean, there's not much more to say to this. And with this, I would like to end this seminar here. And I hope you got an insight over the different ways to describe spins and ensembles of spins. And I hope you learned something. If yes, I would be very happy. And thank you for your real strong attendance. Thank you very much.